600 million years after the Big Bang, something was already there that should not exist. A galaxy, fully formed, glowing with the light of hundreds of millions of stars. The problem? The universe was barely a toddler. There hadn't been enough time, not according to our models, not according to 60 years of astrophysics, for something that massive, that bright, that structured, to exist yet. And yet the James Webb Space Telescope looked straight at it, confirmed it, measured it. It's really there. Astronomers have a name for objects like this. They call them impossible galaxies. And there's not just one. There are dozens, maybe hundreds, sitting in the deepest images of space ever taken, staring back at us like they're daring us to explain them. So tonight, we're going to ask the question that's currently breaking one of the most trusted theories in modern cosmology. What if the universe grew up faster than we ever thought possible? And what if the very first galaxies are hiding something about the origins of everything, including us? Let's go back to the beginning. Not the beginning of Earth. Not even the beginning of the Milky Way. The actual beginning, the first few 100 million years after the Big Bang, a period astronomers call cosmic dawn. For a long time, this era was basically invisible to us. Not because nothing was happening, but because the light from that period has been stretched, pulled, and dimmed by billions of years of the universe expanding. By the time that ancient light reaches Earth, it's not even visible light anymore. It's been shifted deep into the infrared, which means our regular telescopes, even the legendary Hubble, were essentially blind to it. That changed in 2022, when the James Webb Space Telescope opened its golden mirror eye for the first time. Webb wasn't just an upgrade. It was built specifically to see in infrared, specifically to peer through cosmic dust, specifically to catch the faintest, oldest light in existence. Its mirror alone is made of 18 hexagonal gold-coated segments, engineered to unfold in space after launch, forming a light-collecting surface more than 6 times larger than Hubble's. Scientists called it a time machine, and they weren't exaggerating. Because when you look far enough away in space, you're not just seeing something far away, you're seeing something old. Light takes time to travel, so when Webb captures a galaxy 13 billion light-years away, it isn't showing us what that galaxy looks like now. It's showing us what it looked like 13 billion years ago, a live photograph, frozen in transit, from a universe that no longer exists in that form. That galaxy may have merged, grown, or been swallowed by a black hole a billion times over since that light left it. We will never know its present. Only its ancient echo. Here's where it gets unsettling. Before Webb launched, cosmologists had a fairly confident prediction, based on our best model of the universe called Lambda CDM, built on dark matter, dark energy, and gravity slowly clumping gas into stars' galaxies in the first few 100 million years should have been small, faint. Barely they're smudges of a few baby stars clustered together, building up mass slowly, like a snowball rolling downhill, generation after generation, over billions of years. That's not what Webb found. Instead, within days of releasing its first deep-field images, astronomers spotted galaxies that were bright, massive, and strangely mature, dating back to when the universe was less than 500 million years old. One of them, nicknamed a candidate ancient monster, appeared to already contain a mass comparable to billions of suns. Not a snowball, not a smudge, a fully fledged cosmic city, blazing with light, at a point in cosmic history when, according to the math, it simply shouldn't have had time to build itself. Imagine watching a time-lapse of a forest growing. You expect saplings in the early frames. Instead, in frame 1, there's already a 200-year-old oak tree. That's the level of wait, what we're talking about. And this wasn't a one-off fluke either. As Webb kept scanning deeper and deeper into the sky, more of these early, overly massive galaxies kept turning up. Astronomers started calling them little red dots, small in the images, but glowing an unmistakable red from the extreme redshift of their ancient light. Survey after survey found them. Team after team confirmed them. This wasn't a measurement error. This was a pattern. Let's put a face on this mystery for a second, because numbers alone don't capture how strange this really is. One galaxy, catalogued as existing roughly 320 million years after the Big Bang, was confirmed to be so distant that its light left home when the universe was only about 2% of its current age. 2%. If the universe's entire lifespan were compressed into a single calendar year, that galaxy formed sometime around January 8th. And yet it was already glowing. already structured, already unmistakably a galaxy, not a scattered handful of infant stars. Another confirmed record holder, spotted deep in one of Webb's earliest surveys, pushed the boundary even further back, clocking in at just around 290 million years after the Big Bang. Each time astronomers think they've found the earliest possible galaxy, the universe seems to whisper, "Go back further, there's more." So now, scientists are facing a genuinely uncomfortable question. How did the early universe build galaxies this fast? There are few competing explanations, and none of them are fully proven yet. This is where established evidence starts blending into the frontier of active research. So let's be clear about what we actually know versus what's still theory. One idea: maybe star formation in the early universe was simply far more efficient than we assumed. Picture gas clouds in the young cosmos collapsing into stars almost instantly, with none of the braking forces like radiation pressure or slow-forming dust that usually put the brakes on star birth in galaxies today. If early gas converted into stars at a much higher efficiency, you could build a bright, massive-looking galaxy shockingly fast. Another idea: maybe our assumptions about dark matter clumping are slightly off, and the underlying scaffolding of the universe was ready for galaxies to form earlier and faster than the standard model predicts. Dark matter, remember, is the invisible substance that makes up roughly 85% of all matter in the universe. We can't see it directly. We only know it exists because of how its gravity bends light and shapes galaxies. If our map of that invisible scaffolding has even small errors baked into it, the entire timeline of galaxy formation could shift. And then there's a third, more dramatic possibility. Some of the light we're calling galaxy light might not be starlight at all. It might be coming from a supermassive black hole, feeding violently on surrounding gas, blazing so bright it mimics the signature of an entire galaxy of stars. In other words, some of these impossible galaxies might actually be impossible black holes, monsters that grew far too big, far too soon, swallowing matter at a pace that breaks our understanding of how black holes are supposed to form. In fact, one of the most jaw-dropping discoveries to come out of this entire saga is a black hole detected in one of these little red dots, estimated to already weigh in at millions of solar masses, existing when the universe was less than 500 million years old. For comparison, the supermassive black hole at the center of our own Milky Way took over 13 billion years to reach about 4 million solar masses. This ancient black hole appears to have gotten a significant fraction of the way there almost instantly. Cosmically speaking, astronomers have started calling these overmassive black holes because relative to the size of their host galaxy, they're proportionally far too big. It's as if a newborn baby weighed as much as a fully grown adult. Either answer, if confirmed, rewrites textbooks. Either way, the universe built something enormous in a fraction of the time we thought it needed. And we still don't fully know how. Let's slow down for a second though, because there's something almost poetic hiding in this mystery. Every one of these ancient galaxies we're looking at through Webb isn't just a scientific curiosity, it's a message, a photon of light that left its source before Earth existed, before our sun existed, before most of the atoms in your body were even forged. That light has been traveling uninterrupted for over 13 billion years just to hit a golden mirror in space and get funneled into a computer file that a human scientist opens on a laptop with their coffee going cold beside them. Think about that chain for a second. Something happened in a galaxy almost as old as time itself, and it survived every threat imaginable across 13 billion years of cosmic history, just so we could witness it in a single quiet moment. That should give you chills. If it doesn't yet, it will by the end of this video. Now, here's where the mystery deepens even further. These impossibly early galaxies aren't just puzzling because of how big or bright they are, they're puzzling because of what they're made of. When astronomers analyze the light from these ancient galaxies, they can break it apart like a chemical fingerprint and figure out which elements are present. And in several of these early galaxies, they're finding surprising traces of heavier elements. Elements like oxygen, carbon, and even some metals. Why does that matter? Because in cosmology, metal doesn't just mean iron or gold. Astronomers use the word metal to describe basically anything heavier than hydrogen or helium. And here's the key fact. The very first generation of stars in the universe, the so-called population 3 stars, were made almost entirely of just hydrogen and helium, the only elements that existed right after the Big Bang. Everything heavier, everything from the carbon in your blood to the oxygen you're breathing right now, had to be forged later, inside the nuclear furnaces of dying stars, then flung out into space through supernova explosions. That process takes time. Stars need to be born, live out their lives, and violently die before their heavier elements can seed the next generation of stars and planets. So finding meaningful amounts of these heavier elements in galaxies from the universe's earliest few hundred million years means one of two things. Either stars were forming, living, and dying at a stunningly accelerated pace in the early universe, like a cosmic assembly line running in fast forward. Or there's something about early star formation that we still don't fully understand. One particularly strange discovery involves a galaxy where astronomers detected a surprisingly high abundance of nitrogen relative to other elements, a ratio that doesn't match what we'd expect from normal stellar processes at all. Some researchers have speculated this could be a sign of unusual, extremely massive stars burning through their fuel in exotic ways. Others think it might hint at entirely different chemical pathways in the early universe that we haven't fully modeled yet. Nobody has a confirmed answer. It remains, for now, an open case file on the desk of modern astrophysics. Every answer seems to open two more questions. That's what makes this such a gripping scientific mystery. Not that we're clueless, but that we're circling something huge, and every new clue makes the picture stranger, not simpler. And, speaking of strange, let's talk about the darkness that came before all of this light. Right after the Big Bang, the universe wasn't a glittering field of stars. It was almost pitch black. Astrophysicists call this era the Cosmic Dark Ages. For roughly the first few 100 million years, there were no stars, no galaxies, no light sources at all, just a hot, expanding soup of hydrogen and helium gas, slowly cooling in the dark. Then, gravity did its slow, patient work. Denser pockets of gas began to pull more matter toward them. Eventually, in the densest of these pockets, pressure and heat became so extreme that nuclear fusion ignited. The very first stars flickered to life. This moment, the birth of the first starlight in the universe, is one of the most profound events in cosmic history. Scientists sometimes call it "let there be light," only half-jokingly, because it really was the moment the universe transitioned from total darkness to its first flickers of illumination. But here's the part that should genuinely unsettle you. We've never actually seen a confirmed population 3 star. Not one, not directly. These theoretical first-generation stars made purely of primordial hydrogen and helium, potentially hundreds of times more massive than our Sun, burning impossibly hot and bright, and dying young in catastrophic supernovae exist so far only in simulations and indirect evidence. We found tantalizing hints, strange chemical signatures, odd light patterns that might be the fingerprints of these stellar giants. But the smoking gun? A direct, unambiguous image of one? Still missing? It's like knowing your great-great-great-grandparents existed because you're alive, but never having a single photograph of their faces. That's the current frontier. Astronomers are racing to find direct evidence of these first stars, because finding them wouldn't just check a box, it would let us understand precisely how the transition from darkness to light actually happened. And every year, telescopes like Webb push us closer to potentially catching one in the act. There's another phenomenon tangled up in all of this, one that doesn't get talked about enough. The era of reionization. When those first stars and galaxies switched on, they didn't just light up the darkness, they blasted out powerful ultraviolet radiation that ripped electrons off the neutral hydrogen atoms filling the universe, a process called ionization. Over hundreds of millions of years, this cosmic transformation turned the universe from an opaque fog into the transparent, star-filled expanse we see today. Without reionization, light itself would scatter endlessly off neutral hydrogen, and the universe would look like a perpetual, impenetrable haze. Here's the twist. These newly discovered, unexpectedly bright early galaxies might be a major piece of the reionization puzzle. If galaxies were forming faster and brighter than predicted, they may have pumped out enough ultraviolet radiation to reionize the universe earlier than previously calculated. Some studies now suggest reionization was essentially complete hundreds of millions of years sooner than older models assumed. That's not a minor tweak. That's rewriting a whole chapter of cosmic history because a handful of stubbornly bright, stubbornly early galaxies refused to follow the script. Now, let's return to those impossible early galaxies, because there's one more twist that makes this whole mystery even weirder. These galaxies aren't just early and massive. Some of them are shaped strangely too. Astronomers observing the deep universe have noticed a surprising number of these ancient galaxies appear to have a disk-like, almost flattened structure similar to spiral galaxies we see much closer to home, like our own Milky Way. Under the traditional model of galaxy formation, this shouldn't be common so early. Disk galaxies were thought to be a later development, the product of billions of years of gradual mergers, gravitational settling, and cosmic evolution. Finding well-organized, disk-shaped galaxies in the chaotic, turbulent, collision-heavy environment of the infant universe is like finding a perfectly organized library in the middle of a demolition site. One survey using Webb's high-resolution imaging examined a sample of early galaxies and found that a striking majority displayed disk-like structures rather than the chaotic, clumpy, irregular shapes theorists expected. That result alone sent ripples through the astronomical community because it suggests that orderly, rotating galactic structures might be the rule in the early universe, not the rare exception. It suggests that galaxies may have organized themselves into stable, elegant structures far more quickly than anyone predicted. Or, alternatively, that our models of how gravity, gas, and dark matter interact in those first chaotic epochs still have significant gaps. Either way, we're being forced to admit something humbling. The universe's instruction manual for building galaxies might have pages we haven't read yet. Let's take a moment to talk about how astronomers actually confirm any of this, because the process itself is almost as fascinating as the discoveries. When Webb spots a candidate for an incredibly distant galaxy, that's not the end of the story, it's the beginning of a rigorous verification process. Scientists look at how much a galaxy's light has been redshifted, meaning stretched toward longer, redder wavelengths as space itself expands during the light's journey toward us. The more the light is stretched, the farther away and further back in time the galaxy must be. Initially, researchers estimate this redshift using a method involving color filters, essentially checking how a galaxy's brightness changes across different wavelength bands. It's fast, but it's an estimate, and it can occasionally be fooled by other types of objects, like cooler, closer stars, or unusual dusty galaxies that mimic the same color signatures. To get definitive proof, astronomers use spectroscopy, splitting a galaxy's light into a detailed rainbow of wavelengths and looking for specific, unmistakable fingerprints, like the signature emission line from hydrogen gas. When that fingerprint shows up exactly where predicted for an extremely high redshift, there's no more room for doubt. That's how many of these record-breaking early galaxies moved from exciting maybe to confirmed, verified, and published. It's slow, careful, meticulous science, the opposite of hype, which makes it all the more remarkable that even after this rigorous scrutiny, these galaxies keep refusing to behave the way our models say they should. So where does this leave us? It leaves us in one of the most exciting periods in the history of astronomy, because usually, scientific progress moves in small, incremental steps, a slightly better measurement here, a slightly refined model there. But every so often, an entirely new tool reveals a discovery so strange, so unexpected, that it forces a genuine reckoning. That's what's happening right now with the James Webb Space Telescope and the early universe. We are, quite literally, watching in real time as scientists debate whether one of the foundational models of cosmology needs a serious update or a smaller course correction. Some argue that once you factor in observational biases, unusual star formation efficiency, and the possibility of black hole contamination in these bright little red dots, the standard model can be stretched to accommodate what we're seeing. Others argue the anomalies are too consistent, too widespread, and too extreme to explain away, and that we're staring at the first hard evidence that something fundamental about early galaxy formation, or even the nature of dark matter itself, needs to be rethought. There's even a more radical camp of researchers exploring whether these findings hint at problems with our basic cosmic timeline questioning, for instance, whether the universe might be somewhat older than the standard 13.8 billion years, which would quietly solve the not enough time problem by giving galaxies more room to grow. This idea remains controversial and far from broadly accepted. But the fact that serious scientists are willing to question something as fundamental as the age of the universe tells you just how seismic this mystery has become. Nobody knows yet who's right. And that uncertainty, that genuine open question sitting at the frontier of human knowledge, is what makes this moment so electric. This isn't settled science being repackaged for entertainment. This is live, unresolved, cutting-edge research, the kind of mystery that could, within the next decade, completely reshape our understanding of how the universe assembled itself. And there's something deeply moving buried inside all of this technical uncertainty. Every one of these galaxies, every impossible little red dot, every whisper of an ancient disk structure represents billions of stars and potentially trillions of planets. Existing at the very dawn of time, worlds that may have risen and fallen, whole cosmic histories playing out long before Earth was even a swirling cloud of dust around a young, unremarkable star. We are, in a very real sense, looking at our own ancestry. The same processes that built those first strange, oversized, precocious galaxies eventually, after billions of years of mergers, explosions, and quiet cosmic patience, built the Milky Way. Built our sun. Built the atoms that make up your body, your brain, the thoughts you're having right now as you listen to this. Every carbon atom in your cells was forged in the heart of a dying star. Every oxygen atom in the air filling your lungs came from a stellar explosion older than our entire solar system. When you look up at these ancient galaxies through Webb's data, you're not looking at some distant, unrelated cosmic curiosity. You're looking at the earliest chapters of your own origin story. And the truly wild part? We're still on page 1. Because as powerful as Webb is, it's already hinting that even more extreme surprises might be waiting just beyond its current reach in the redshifts we haven't fully explored yet, in the epochs even closer to the Big Bang than we've managed to see. There's already discussion within the astronomical community about upcoming missions and next-generation ground-based telescopes equipped with even more sensitive infrared detectors, designed specifically to push past Webb's current limits and potentially catch a glimpse of the true cosmic dark ages the moment right before the first star switched on. If that happens, if we ever manage to directly observe the very first flicker of starlight in the history of the universe, it won't just be another data point. It will be, in a very real sense, humanity witnessing its own creation story unfold in real time, 13.8 billion years after the fact, from a small blue planet that didn't even exist yet when the light first began its journey. So here's the truth we're left with tonight. The universe's first galaxies shouldn't exist, not the way we're seeing them. Not this early, not this massive, not this organized. And yet, there they are, glowing steadily across 13 billion years of empty space, patiently waiting for a species clever enough to build a golden mirror and point it at the darkness. We built that mirror. We pointed it at the beginning of everything, and what stared back at us wasn't the simple, orderly infancy we expected. It was something stranger, something faster, something that suggests the story of how we got here is far more astonishing and far less understood than we ever dared to believe. Every impulsible galaxy is a question mark burning in the dark, 13 billion years old and still unanswered. Every little red dot is a challenge thrown at everything we thought we knew. And somewhere out there, in redshifts we haven't reached yet, in wavelengths we haven't fully explored, there are more of them waiting. More impossible things. More questions bright enough to break our best theories all over again. The universe is still keeping secrets, but for the first time in history, we finally have the tools to start pulling them into the light. And if the last few years are any indication, what we find next might be even harder to believe than everything you just heard.